we will continue with one more problem, tutorial problem on log mean temperature difference, shell and tube heat exchangers and dot factors. So, the specific problem that we are going to deal with, a heat exchanger with the process streams, that is the inlet fluid and the outlet fluid are specified. The temperatures at the inlet and outlet are also known, the flow rates are known, and the shell and tube heat exchanger provided is a 1-4 heat exchanger. That means one shell pass and 4 tube passes. The properties are also provided. The heat transfer coefficient on the outside, that means on the shell side, is provided, and more importantly a value of the dart factor, that is the resistance due to the deposition of materials on the inside as well as on the outside of the tubes, which would provide a significant amount of additional heat transfer resistance that is mentioned. So, the specific heat exchanger that is designed has some dart factor. It must provide a value of a dart factor. It should work with a dart factor that is provided in the statement of the problem. What that means is that if our calculations show that a dart factor that we obtain from our calculation is more than the dart factor which is to be provided in the design of it, then the system should work, because the system can handle a higher value of dart factor than the specified one. So, the heat transfer or the heat exchanger would work. So, the problem I have described it over here, and then I will slowly go through the problem, the solution, and some of the concepts which would automatically appear out of the solution of this problem. So, this problem is about log mean temperature difference, multi-pass heat exchanger. The value of dart factor is provided. We need to calculate the dart factor for this specific situation at hand and then make a decision about the suitability of the heat exchanger for this specific purpose. So, let us look at the problem over here. It's a problem on log mean temperature difference and dart factor. So, what we have is a shell and tube heat exchanger. So, the outside one that we see is the shell, and the green line which you see, so this is the shell, and in the shell side 20,000 kg per hour of kerosene at 200 degree centigrade is entering, which is being cooled to 94 degree centigrade. So, the mass flow rate of kerosene and the delta T, T inlet and T outlet, that is provided. It is a 1-4 heat exchanger. So, the tube side fluid enters, completes the second pass, this is the third pass, and then comes out after it crosses the shell 4 times. So, that is why it's the 1-4 shell and tube heat exchanger. That means 1 shell pass and 4 tube passes. On the tube side, we have crude oil, which is the tube side liquid, which enters at 38 degree centigrade and leaves at 77 degree centigrade. So, this is 38, it leaves at 77, and the shell side is at 200 and it leaves at 94. It has been mentioned that the heat transfer coefficient on the shell side, which is H suffix O, is 920 watt per meter square Kelvin. There are a total of 160 tubes, that means 40 tubes per pass. So, that is the number of tubes per pass which is present in the shell and tube heat exchanger. The tubes are 4.88 meter long. The internal diameter is provided, and the total heat transfer area of these tubes is given as 61.5 meters square. The properties of crude oil, which provide the viscosity, the specific heat, and the Prandtl number is given. So, it has been mentioned that this shell and tube heat exchanger should provide a combined dart factor of this much, 5.8 into 10 to the power minus 4. So, based on the data which are provided in here, we have to make a judgment of is the heat exchanger suitable for this operation. That means these conditions, do they require can they handle a dart factor even higher than this or a dart factor lower than this. So, if these calculations, if calculations based on these data provide an overall dart factor which is less than the dart factor which is provided by the heat exchanger, then we have a problem. Then it cannot handle, it won't be able to handle the specific operation. So, we have to first calculate what are the the first step would be to find out what is the log mean temperature difference. So, once we calculate the log mean temperature difference, we should also be able to calculate what is the heat transfer coefficient on the tube side based on the Reynolds number and Prandtl number of the crude oil that is provided. So, we have the LMTD, we have the heat transfer coefficient, so on the inside, and the heat transfer coefficient on the outside is provided. So, combining these two together, which is 1 by HI and 1 by HO, heat transfer coefficient on the inside as well as on the outside, would give me the value of UC, or overall heat transfer coefficient, which is called also known as without any dart, which is also known as the clean coefficient. So, we have a clean coefficient now, and this clean coefficient would have to be used in order to find what is the RD, the dart factor for this specific case. Now, for the dart factor, one has to equate Q, that is the total amount of heat that is transferred, is equal to U A delta T log mean. This U that we would use is the U based on the dirty condition present inside the heat exchanger. So, this delta T first, the log mean temperature difference first will have to be modified to make it applicable for multi-pass heat exchangers. So, the LMTD based on pure counterflow has to be converted into the corrected LMTD by the incorporation of the factor F, the correction factor that we have discussed before. So, Q is equal to U A delta T, and Q is simply m dot Cp delta T, T2 minus T1. The m dot for the tube side fluid is known to us, Cp of the tube side fluid and delta T of the tube side fluid is also known to us. So, m dot Cp delta T all for the tube side must be equal to UD, where UD is the UD is the value of the dirty condition overall heat transfer coefficient, times A being the flow cross section, A being the heat transfer area, times corrected value of delta T. This should give me the value of UD, because that is the only unknown in the equation. Then comparing UC and UD, we should be able to arrive at the value of the dart factor. So, let us go do the step by step calculation and see how we can arrive at the value of the dart factor which this specific operation demands, and whether or not what would be its value relative to the dart factor to be provided by the heat exchanger, and only then we can make a judgment of whether this heat exchanger it is possible to use this heat exchanger for the transfer that we have just described. So, let us start with the calculation of LMTD first. So, when we look at the solution of this, the things that are provided first is the value of HO is 920 watt per meter square Kelvin. The thermal conductivity K of the crude oil would be from the Prandtl number, from the known value of the Prandtl number, the value of K would simply be 2.0516 So, it's simply by putting the values of Cp, mu and Prandtl number, one would be able to obtain K to be equals 0.133 watt per meter Kelvin. Now, I need to calculate LMTD, and since it is a multi-pass heat exchanger, a corrected value of LMTD is to be used. So, in order to obtain the corrected value, I have to multiply the LMTD by the factor F, which we have described. In order to do that, this LMTD is to be calculated based on counter flow. So, if we go back to this figure once again, based on counter flow, then what we have is as if the whole fluid is moving in this direction. Instead of these 4 passes, I just have one pass where the crude oil enters from this side at 38 and it leaves on the other side at 77, and the shell side fluid comes at 200 and flows counter to the fluid and leaves at 94. So, the modified figure for this would be this being the heat exchanger, the shell side fluid comes at 200, it leaves at 94, and the tube side fluid comes at 38 and leaves at 77. So, this is the pure counterflow representation of the previous figure. So, therefore, the LMTD would simply be 200 minus 77, which is the delta T at this point, minus 94 minus 38, which is the delta T at this point, by ln of the difference. So, once you calculate that, this LMTD based on counter flow would turn out to be 85.15 degree centigrade, and since it is a 1-4 exchanger, 1-4 heat exchangers, so correction needed for LMTD and in order to calculate the correction, in order to use the results which are available in your text in the form of figures. So, you need to calculate P2, which is T2 minus T1 by T1 minus T1. So, T2 minus T1 is that of the cold fluid. So, which is coming at 38, leaving at 77, and this T1 is the hot fluid which is entering, and this is the cold fluid which is entering. So, this is 38, which would be about 0.24. Similarly, one can calculate the other parameter in the graph for finding out the correction factor for LMTD. This R is defined as T1 minus T2 by T2 minus T1, which is equal to the entry temperature of the hot fluid, the exit temperature of the hot fluid, the exit temperature of the cold fluid, and the entry temperature of the cold fluid. So, when you do that, it is going to be 2.72. Once you use these two and use the from graph, you would see that the correction factor for the temperature would be equals 0.85. So, in that case, the delta T actual would be the LMTD based on counter flow multiplied by the correction factor, which is 85.15 into 0.85, which is 72.4 degree centigrade. So, this is going to be the corrected value of the heat transfer, corrected value of the temperature difference. So, this part is over, and now we have to see what is going to be the I know HO to be equals 920 watt per meter square Kelvin. what is going to be the value of HI. So that is my next step. And in order to do that, I am going to use the relation which we have seen many times, the Dieter's-Boulter equation, Reynolds number based on diameter to the power 0.8 and Prandtl number to the power 0.4. So, in order to calculate Reynolds number, I understand that I have 40 pipes per pass. So, if I equate if I try to find out what is the mass flow rate through all these 40 pipes in a pass, which is rho times area, cross sectional area of one pipe. So, pi d square by 4 multiplied by n number of such pipes multiplied by u, this must be equal to m dot of the cold fluid. Once again, the mass flow rate of the cold fluid can be calculated based on area, cross sectional area multiplied by u, which would give me volumetric flow rate through one tube, multiply with n, the number of tubes per pass. This is going to be the volumetric area of the this is going to be the volumetric flow rate of the cold fluid entering into the heat exchanger. When I multiply it with rho, this becomes the mass flow rate of the cold fluid entering into the shell and tube heat exchanger. And this we know to be equal 67,600 by 3600 kg per second. As in the problem statement, it was mentioned that the crude oil the crude oil is 600 kg per hour. So that's the flow rate of the crude oil which enters the shell and tube heat exchanger. Since there are 1/4 passes, so if I consider there would only be 40 tubes which are available for this much of crude oil to flow. So what I am trying to do in this case is trying to find out what is this unknown velocity u for flow through the pipes. So everything here is known. I would be able to calculate what is the value of u, or rather u rho, which would be 1436.26 kg per meter square per second. Why I am keeping it as u rho? Since my Reynolds number is going to be d u rho by mu. So, I already know what is the value of u rho, which is the value for d, the value for u 14 and the viscosity of the crude oil. So, 8148. So, therefore, this is definitely in the turbulent range, and since in the turbulent range, that's why the Dieter's-Boulter equation can be used, and it's a problem of heating. So, that's why Prandtl number, heating of the cold tube side fluid. So, therefore, the Prandtl number has the exponent equal to 0.4, otherwise it should be equal to 0.3. So, with the value of Reynolds number and with Nusselt number to be equals this from Dieter's-Boulter equation, this would give you the value of Nusselt number to be equals 154, and this would give you the value of the heat transfer coefficient on the inside to be equals 154 into the value of K by the value of D, 1006 watt per meter square Kelvin. So, this is another important result, that I know what is the value of my HI. So, 1 by UC, the clean coefficient, the overall heat transfer coefficient based on the clean condition. So, there is no effect of RD or the dart factor, it is just the algebraic sum of the resistances of the convective heat transfer resistance on the inside, that is the tube side, and convective heat transfer resistance on the outside, which is the shell side. So, this would give us the value of UC to be equals 480.5 watt per meter square Kelvin. So, this is nothing but the clean heat transfer coefficient. So once I know the clean heat transfer coefficient, then the next step is to find what is the heat transfer coefficient for a heat exchanger which has been in use for quite some time, such that the dirt factor resistance, the resistance due to the dirt deposited on the tube and on the outside of the tube, must be taken into account. So in order to calculate the dirty coefficient, I know that my value of the heat transfer area provided is 61.5. So UD, the dirt heat transfer coefficient, is Q by A delta T, and Q is simply m dot Cp delta T for the cold as well as for the hot, but we are going to use the cold over here. It does not matter. So this is must be equal to m dot Cp delta T for the hot side as well. So we are using the cold side in this specific case, but you could have used the hot side as well. So m dot of the cold side fluid, which is 67,600 by 3600, Cp for the cold side 2.05 into 10 to the power 3, and delta T, that is the temperature rise of the cold side, which would be 77 minus 38. So from 38 the cold side fluid temperature has risen to 77. The area is 61.5, and the delta T, this is the corrected value of the log mean temperature difference, which we have calculated to be 72.38, and therefore UD is 337.4. So from our previous calculation, we have found UC to be equals 480.5 watt per meter square Kelvin. The point to note here, obviously for obvious reasons, the heat transfer coefficient for the cold side is going to, for the clean operation, is going to be more, significantly more than the heat transfer coefficient when the entire system is in operation for some time. So the clean coefficient, when everything is clean and there is no dirt factor, no resistance due to deposition, is going to be more than that of the dirty coefficient when we have to take this into account. So the relative values of the dirt factor, relative values of the clean coefficient and that of the dirty coefficient would give us some idea of what this dirt factor is going to be. We also understand that this dirt factor can be treated as a resistance which simply gets added to the overall resistance due to the clean coefficient. So the clean coefficient consists only of Hi and Ho, provided we assume that the conduction resistance through the tubes is small. So 1 by Ho plus 1 by Hi plus Rd is equal to 1 by Ud. So that dirty coefficient takes into account three resistances, whereas the clean coefficient simply takes into account of Hi and Ho, 1 by Hi and 1 by Ho. So knowing the two values of the clean coefficient and the dirty coefficient, one should be able to find out what is the value of the dirt factor for this specific operation, and then compare that with whatever dirt factor the exchanger must provide as per its design. So our next step then simply is to find out what is the value of the dirt factor. So let's see what this value would be. And your Rd calculated for this specific purpose, since I know Ud and Uc, and so this 1 by Uc, 1 by Ud must be equal to 1 by Uc. plus RD, that is 1 by U dirty, is going to be the resistance due to the clean condition plus RD, which is the dirt factor. So, your RD would simply be equal to UC minus UD divided by UC UD, and this would give rise to RD calculated to be equals 8.8 into 10 to the power minus 4, and we can see that this RD calculated is greater than the RD which is the required one. The RD required is provided at the beginning in the statement of the problem, that the combined RD factor should be 5.8 into 10 to the power minus 4. So, RD required is 5.2 into 10 to the power minus 4. So, therefore, what it shows is that the calculated RD which comes from the stable operation of the heat exchanger is more than the designed one. So, this heat exchanger can then definitely handle a situation which is more than the RD which has been provided for this heat exchanger. So, that means in other words, the heat exchanger can then handle dirtier fluids as compared to the designed one. So, we have obtained we have calculated the dirt factor based on the stable operation of the heat exchanger, including kerosene and crude oil, and what we see is the combined dirt factor for that operation is more than the designed one. So, the heat exchanger operates perfectly even when its dirt factor is more than the designed one. So, the conclusion of this problem would be yes, this heat exchanger can be used for the designed designed dirt factor and even beyond that. So, the problem then therefore gives us an idea of the log mean temperature difference, the corrected values of the log mean temperature difference, evaluation of the Reynolds number, choosing of the correlation to be used for calculation of HI, the inside heat transfer coefficient, combining HO and HI to give us the value of the clean coefficient. From the process data, calculate what should the RD, the dirt factor, would be. The dirt factor is simply going to be a combination of the clean coefficient and the dirty coefficient, and these then can be used to decide about the applicability of the heat exchanger for a specific operation. So, this concludes our study on log mean temperature difference and its use in heat exchanger calculations. But the log mean temperature difference, if you think once again, requires the 4 temperatures to be known, especially the inlet and the outlet temperature of the hot fluid and the inlet and the outlet temperature of the cold fluid must be known to us. If one is unknown, then through heat balance we will probably be able to deduce that, but all 4 temperatures need to be known in order to proceed for heat exchanger design utilizing LMTD, because the first step in heat exchanger design is to find the log mean temperature difference. So, if I do not know the 4 temperatures, I cannot proceed. So, this under many circumstances we would know only the inlet temperatures, the outlet temperatures are not known to us. So, the procedure based on LMTD would not be straightforward to use, we would not be able to use LMTD method. So, we need to find an alternative method to go for the design of heat exchangers where the temperatures of the 4 streams are not known. What that would be, what that approach would be, we will see in the next class.